Good afternoon. It's my pleasure to introduce today's speaker, Chang from Carnegie Mellon University, where she's completing her PhD sometime this summer, I guess. And Faye has been working in operating system, I/O, and other network devices, and so on. So today she's going to talk about automatic I/O prefetching hints for speculative execution.
Good afternoon. Thank you all for coming. I'm going to be talking about some of my thesis work on automating I/O prefetching. This is work that I've been doing with my advisor, Garth Gibson, at CMU. And I would welcome questions at any time during this talk, so please feel free to just jump right in. So we all know that disks are slow, but I'd like to begin by just reminding everyone of exactly how slow they are. So disk access takes on the order of a millisecond. This is equivalent to hundreds of thousands or even millions of processing cycles. That's a lot of processing cycles. And far from diminishing, this gap between processing speeds and disk access rates is growing, and it's growing rapidly as shown in this graph, because while processing speeds are doubling every 18 months, disk access rates are only improving at around 10% a year. Now, some people have predicted that growth in memory sizes would make disk latency less of an issue. Well, in general, this has not turned out to be the case, because data sets and data objects are growing, and we're continually introducing these new data-intensive applications. So for example, in 1991, Mary Baker published a paper on the traces of the sprite file system, in which she reported cache miss rates of around 40%. Well, just last year, a paper was published on traces of the NT file system, and they reported cache miss rates still around 40%. So, of course, these traces were taken in very different environments, but it serves to illustrate the point that disk latency is still very much of an issue. So common approach to hiding latency that is used at all levels of computing systems is to perform prefetching. That is to fetch data before it is needed so that it will be available at a lower latency. Now in terms of I/O, most systems perform read-ahead, which is just sequential file prefetching, but read-ahead often is not effective. So as the file traces have shown, many read accesses are random, and many sequential runs are short, such that they could even fit within a single cache block. So in order to be effective at prefetching, what the system really needs is very accurate information about what data will be needed in the future early enough to hide the latency of fetching that data. Well, previous research has shown how to obtain this very accurate information from looping array codes by statically analyzing these very regular codes. But many applications, many data-intensive applications, particularly those that we might expect to see used in personal computing, have more complex control and data flow. Now, previous research has also shown that we can significantly improve the performance of these more generic data-intensive applications through prefetching. So for example, Hugo Patterson showed 20 to 70% improvements for the TIP benchmark suite, which consists of a number of real-world applications. But these improvements were demonstrated by manually modifying the benchmark applications such that they would explicitly provide the information about what data they would access in the future. And of course, manual modification can be very costly because it can consume a lot of programming effort. So what I did in my thesis work was to propose a new approach to automatically predicting the future data needs of applications, of generic data-intensive applications. And this approach is based on an observation that we can often trade off between resources that are more expensive in order to improve the performance of parts of the system that are normally bottlenecks. So the problem of I/O prefetching actually decomposes into two subproblems. And one is this problem of predicting the future accesses of applications. The second part of the problem is how do we schedule prefetches given that we have accurate predictions. I actually take advantage of an existing solution for the prefetch scheduling problem. I use the system that Hugo developed in order to demonstrate these performance improvements. And I concentrate on the previously unsolved problem of actually making those predictions. My approach to predicting the future data needs of applications is based on the observation that when an application is stalled on I/O, it will often be the case that there will be some spare processing cycles. So maybe there's some way we can use these spare processing cycles to somehow hide some of the latency that will be experienced by these stalled applications. So in particular, my approach is based on two hypotheses. The first hypothesis is that we will often be able to identify the future data needs of applications simply by pre-executing that application's code, even though during this pre-execution, we will not have the data that has not yet been fetched from disk. So I'm proposing that we add this extraneous execution to the application, and I don't want to hurt the performance of any concurrently executing applications. So the second hypothesis is that there will often be enough spare cycles on our system such that this pre-execution can be effective. That is, that it will predict the future data needs early enough to hide the latency of fetching the data. To make this a little more concrete, let me run through a very simple example. Say that we have an application that issues 4 read calls for data that does not reside in the file cache. Well, its execution will look something like this. It will begin processing until it issues its first read call, which will miss in the file cache, causing a disk request to be initiated. And then it will stall, waiting for this disk request to complete. When the request completes, it will get to process for a little while, but only until it issues its second read call, because this read call will also miss in the file cache, causing another I/O stall. And this cycle of a little bit of processing and then an I/O stall will continue 2 more times before the application completes its execution. Now say that we instead add speculative execution to this application. Well, then its execution would look more like what's shown here. So it would begin its execution processing until it issues its first read call, which would miss in the file cache, causing a disk request to be initiated. But instead of simply stalling and waiting for that disk request to complete, the execution of the application would continue speculatively as if the read call had completed successfully. So that, for example, this green bar here would correspond to that green bar there in terms of the execution. And during this speculative execution, whenever it encounters a read call, it would instead initiate a non-blocking prefetch call, which ideally would cause the data to be fetched in parallel with the original request. Meanwhile, the speculative execution would continue, issuing more prefetch calls as it encounters more read calls. Now, when the original data request completes, the normal execution of the application would resume, and it would continue as if the speculative execution of the application had never occurred. However, now when it goes to read its data, it may discover that it's already in the file cache because it has been prefetched during the speculative execution, such that in this example, all of the remaining read calls of the application would hit in the file cache, and the execution time of the application would be more than halved. So this is a very simple example, and I wouldn't be surprised if many of you were feeling a bit skeptical. What about data dependencies in the applications, for example? But even though it sounds like kind of a crazy idea, it actually works. So this is a quick flash forward to some of my results. On the y-axis here, I have the % performance improvement with the speculative execution approach. And I have results here for 6 applications, and these are all real-world applications. For example, Sphinx is a speech recognition system. P20% and P80% are the Postgres relational database. And what this graph shows is not only does the approach work, but it works very well. We've got performance improvements from 6% up to 72%, with 4 of the 6 above 50%. So very significant improvements. Yes?
This assumes, of course, that only those programs are running, or they're running one
Yes.
at a time. So normally one would think of you pause for a disk I/O, but you really don't pause, that you're really executing some other thread or process on the machine.
Yes.
When you have that, how common is that scenario, and how does it affect the results that you're showing here?
So there's been a lot of other research on idle cycles and machines, and I won't reiterate that. But I do have some results that I'll show you at the end of this talk for how well this approach works when there's a lot of competition for CPU. To give you a quick idea of what's coming up with the talk, that was kind of the introduction. what I'm going to do now is to describe one particular way of adding speculative execution to applications. And this is a very basic design. It's kind of the bare minimum of what you need to just get speculative execution to work. And then I'll show you some results for this naive design. And then I'll describe some techniques for making speculative execution a little more sophisticated. So the name of the design that I'm going to describe is the Specant design, and it relies on binary modification. So it does not require any application source code, and this is very important because in many cases application source code is not available. It also does not require any special operating system support, though of course if such support exists it can take advantage of it. A basic element in the design is the addition of a thread to the application. And this application is responsible for performing all of the speculative execution that's performed on behalf of that application. So I'll refer to this as the speculating thread. The speculating thread's execution is constrained by just assigning it the lowest possible scheduling priority. And it initiates prefetching by issuing prefetch hints to the prefetch scheduler. Now in my implementation, as I mentioned earlier, I take advantage of an existing prefetch scheduler, which actually resides in the operating system. But a very basic version of the prefetch scheduling function could have easily been incorporated within the user level design, and it should not change any of the numbers that I will show you in the course of this talk. Now, as with all optimizations, there are three basic design goals. First, we want the design to be safe. That is, we don't want to change the results of executing the application. We also want the design to be free in that we will not be hurting the performance of either the target application or any other concurrently executing applications. And finally, we would like the approach, of course, to be effective in that it will substantially improve the performance of a range of applications. So what I'm going to describe next are some of the mechanisms I use to achieve these design goals. Now, in terms of safety, there are two things that make achieving the safety difficult. The first is that when the speculating thread is executing, it may be using data values that are incorrect because it does not have the data that has not yet been fetched from disk. And the second is that when the original thread resumes its execution after an I/O stall, it expects to continue as if the speculative execution had never occurred. So we have to be very careful not to mess up the state of that original execution. So there are four things that the speculating thread must not do. The speculating thread must not modify any of the data values that will subsequently be used during the normal execution of the application. The speculating thread must not issue any unsafe system calls, like, for example, a write system call that would modify the file system. The speculating thread must not generate any exceptions that will disrupt the execution, the normal execution of the application by, for example, prematurely terminating that process. And finally, the speculating thread must not receive any asynchronous signals that were really meant for the normal execution of the application. So in addition, because I'm relying on binary modification, there are a few potential safety holes that I do allow with this design. The first is that with binary modification, I change the memory layout of that binary. So if, for example, your binary, if you had some memory bugs in your application, I may expose bugs that were previously untriggered. And second, I will be changing the dynamic resource consumption of the application. So if your application depended on this information for some reason, for example, if it depended on timing information, then I could be changing the results of executing this application. Now, these are often considered to be not an issue. If you are concerned about them, I do have an alternative design that does not present these safety holes that I will not be discussing during the course of this talk, however. So what I'm going to do now is talk about the mechanisms that I use to ensure that the first four do not occur. So the first potential safety hole was that the speculating thread could change the data values that are used during the normal execution of the application. To prevent this from happening, I have the speculating thread perform software copy and write. Now, software copy and write is almost identical in function to hardware copy and write, or OS copy and write. Memory is divided into regions, and the first time that the speculating thread issues a store to a region, it makes a copy of that region and redirects the store to that copy. Any stores and loads to regions that have already been copied are simply redirected to that copy, whereas loads to uncopied regions are allowed to proceed without any redirection. So typical copy and write, and that does minimal copying, basically. Now, one of the differences is in terms of its implementation. Software copy and write is implemented by adding software checks before all the load and store instructions that might be executed by the speculating thread. And these checks keep track of the mapping between the original data regions and their copies and perform the redirection as appropriate. Now, memory operations consist of 30% or more of the instructions that are executed in a typical instruction stream. So if I were to add a check before every load and store operation and then force the original thread of the application to branch around each of these checks, well, then I would be adding a significant amount of overhead to the normal execution of the application. To avoid all this excess branching, what I do is make a complete copy of the code of the application, which I refer to as the shadow code. And then I constrain the speculating thread such that I can only execute shadow code. This allows me to only add software copy and write checks before the load and store instructions in the shadow code. And the original thread, which executes the original code, doesn't need to do any extra branching instructions.
Why do you need the copy and write if you have shadow code to separate it from the original code?
The copy and write protects the data state of the application. The shadow code is there to allow copy and write checks to be added without adding overhead to the normal execution of the application. It does not protect the data state by itself. Okay.
And once again, the checks are to see whether or not you're writing. What are the checks again?
The checks see whether or not, if it's a store operation, it depends on what it is, but basically it takes care of the copy and write function. It checks to see whether or not the region that is being touched has already been copied, and then it redirects the store or load as it should, basically. Yes?
Do you perform any optimizations to avoid redundant checking?
Well, there's some simple optimizations that I do perform. For example, I don't have to do software copy and write for, I don't have to add checks before stores and loads off the stack pointer. And I instead check the stack pointer. So things like that. But I actually don't do any more sophisticated static analysis that would be possible. So the second potential safety hole was that the speculating thread could issue unsafe system calls. I take a very conservative approach to avoiding this problem. I basically constrain the system calls that the speculating thread could issue. In particular, the speculating thread issues hint calls. It actually replaces read calls with these hint calls. And it also is allowed to execute fstat calls and dynamic memory allocation. But it skips all other system calls such that they cannot possibly present a safety problem. Now, the third possible safety hold was that the speculating thread could generate exceptions that would disrupt the normal execution of the applications. To avoid this situation, I have the speculating thread install signal handlers such that it catches any exceptions that it may generate and handles those exceptions. Now, remember that the speculating thread is actually prone to generating exceptions because it may be using some incorrect data values. So this is very necessary. And finally, in order to prevent the speculating thread from catching signals that were meant for the normal execution of the application, I have the speculating thread mask all other signals so that they will be delivered to that original thread. So these are the four mechanisms that I use to ensure the safety of the design. The other important part of the design, the other necessary part of the design, is in terms of hint generation. So if you think of speculative execution, if you just start the application and you begin speculating, there are two obvious scenarios that may occur that will cause speculative execution to be very ineffective at hint generation. So these two scenarios are if the speculative execution falls behind the normal execution of the application, such that the speculative execution will have to catch up to the normal execution before it can generate any useful hints. And the other scenario is if the speculative execution just completely does the wrong thing, right? For example, if it performed a conditional branch using a data value that is incorrect, and such that not only will it fail to generate correct hints, but it may generate a large number of incorrect hints. Now, if either of these two scenarios occur, what we would really like is for the speculative execution of the application to resynchronize with the original execution of the application, where resynchronizing the speculating thread means to modify the speculating thread's execution state such that it will appear to be picking up from the point in the execution from where the original thread is currently stalled, so that it will have the most up-to-date data state with respect to the normal execution of the application. Now, there's two problems that have to be solved in order to do this resynchronization. The first is you have to detect when to resynchronize the speculative execution with the original execution. And the second is that you have to actually have a process for performing the resynchronization. In order to detect when to resynchronize, I use a hint log data structure. Basically, the speculating thread logs each of the hints it generates. And before the original thread issues a read call, it checks the hint log. Now, if there's no next entry in the hint log, or if the entry in the hint log doesn't match the read that's about to be initiated, well, then it knows that one of these two situations has occurred, so it sets the resynchronization flag. And the speculating thread discovers that it needs to resynchronize simply by polling that resynchronization flag. So that takes care of the detection. And what about the actual process of resynchronizing? Well, since these two threads reside in the same address space, the only state that I need to expose explicitly in order to resynchronize is the register state of the original thread. So when the original thread sets the resynchronization flag, it dumps its register state into a data structure that the speculating thread resynchronizes by grabbing this register state. Then it makes a complete copy of the original thread's stack using the stack pointer that is saved within this register state information. And it clears its software copy and write state. And then it jumps to the instruction after the read call in the shadow code. And at that point, if it continues, it will look like a continuation of the original execution of the application. So as I said earlier, I implemented this using binary modification. In particular, I implemented a binary modification tool that I call the Specint tool. The process of transforming an application to use speculative execution is fairly straightforward. I take the application's object files and any libraries, and I link it using the standard linker with the libraries for threading, since I'm adding threads to the application, and some Specint auxiliary object files, which contain things like the initialization routine for spawning the speculating thread. Then binary is munged by my Specint tool, which produces a new binary that can be processed by the standard linker to produce a speculating application executable. Now, my evaluation platform is actually a little bit out of date right now. It's a 233 megahertz alpha workstation running digital Unix with the tip prefetch scheduler that I mentioned earlier. And the data for the applications is striped across some number of disks. And I have numbers for all combinations between 1 and 10, but I'm only going to show you the results for the 1-disk case and the 4-disk case. For all the cases between 2 and 10 look essentially identical to the 4-disk case, except that the magnitude changes slightly. The only ones that were critically different were the 1-disk case and the multi-disk case, and that's why I'm only showing you those two sets of numbers. I use the tip benchmark suite to evaluate my technique, which consists of XDataSlice, a scientific visualization tool that basically performs strided accesses through a very large data set. Then agrep, which is text search, so it sequentially reads a very large number of small files. GNU-LD is an object code linker, so it performs multiple passes through all of the input files, reading different portions of each file during each pass. And these are data dependent. In Postgres, 80% and Postgres 20% are both relational database joins. The difference in the 80% and the 20% is basically the percentage match. So you can think of this as being more data and think of this as being less data. And finally, Sphinx is a speech recognition system. Now, interesting things about this benchmark, well, they're all real-world applications. None of them were created just to be a benchmark. Almost all of them are fairly large and fairly complex. And one of the primary reasons that I chose this benchmark was that I have versions of each of these applications that were manually modified to issue prefetching hints, so that I could compare my system not only against the results that you would obtain simply by running a non-prefetching version of the application, but also against kind of the ideal performance that you could obtain if you went through the trouble of manually modifying your applications to do prefetching. Yes?
Clean disk, use the clean disk.
Excuse me?
That is, the data is optimally laid out on disk.
I don't know if it's optimally laid out. It's actually just striped. You take the data set and you just stripe it, basically.
But there wasn't any other data on the disk. So what might typically happen on a regular disk is fragmentation that would tend
Right. No, I did not do any kind of artificial aging of the file system. Yes. So to look at some results, I'm going to show you a series of results graphs through this talk. They'll have very similar axes. The y-axis here is the % performance improvement over the non-hinting original application. The non-hinting original application in all of my numbers actually takes advantage of the read-ahead policy of the operating system. So it does get to benefit from some prefetching. And the blue bars in all of my graphs will be the performance of the naive design that I just described to you. And the green bars will be the performance of the applications when they were manually modified to perform prefetching. So if you, let's see. The graph on the left is for the one disk case, and the graph on the right is the 4 disk case. And of course, when you have multiple disks, prefetching benefits because it can overlap IOs, right? Whereas in the one disk case, you can only overlap prefetching with the CPU processing of the application. So there's not as much benefit. Now, if you just look at the height of the blue bars across these graphs, you'll see that there are very substantial performance improvements, particularly when you have multiple disks. In fact, for 2 of the 6 applications, Xdata Slice and agrep, the performance improvement with this approach is almost as good as what you would obtain by manually modifying these applications. Of course, these results are not perfect. For example, there's this huge performance loss for GNU-LD on the one disk case. And also, there's a question of why there's a difference, such a difference between performance of naive speculation and manual modification in many cases. Mm-hmm.
When you compare, I mean, it's kind of unfair to compare against Unix prefetch, the standard Unix prefetching algorithm is well known not to be the best you could do. So did you compare against something like Griffin and Appleton, or that is ones that maintain a more sophisticated, prefetching algorithm inside the kernel?
Actually, I did not. Something like Griffin and Appleton would not necessarily work for these applications because these are data-intensive applications. They would need to store a lot of, log a huge amount of history information in order to usefully predict the future data needs. Also, Griffin and Appleton's work did whole file prefetching, or they did it, they tracked it on a file basis. So it's difficult to do history-based prefetching for these types of applications.
Well, let me put it a different way. That is, do you have a sense of, if one were to do a observation-based prefetching scheme that knew nothing about the behavior of the program except what it observed and had no hints, how much better it would do than normal Unix prefetching? In particular, if I'm normally accessing little files,
right.
But I can observe in my kernel that I'm stepping through all the files in a directory, for example, then it's pretty easy for me to build in the intelligence that's going to be needed to read in those sets of files.
Okay. So all I know is what's been published in the literature, and I've talked to a few of the people who worked on these history-based techniques before, and they have numbers. Their measurements are different, of course, because with history-based techniques, you normally want to acquire this information over a long time, not only the execution of a single application.
Sure.
So the numbers that I've seen are things like 5 to 7% improvement for the file system performance for the file system prefetching, and then the results for within the single run of an application for paging applications has not really been thoroughly investigated, but it hasn't been, it's nowhere near the numbers that you'll see here, basically.
I'm a little late in asking this question. When you resynchronize and you have a wrong hit,
Yes.
okay, but you have your speculative execution has gone ahead and has brought in other strikes. Do you throw these away?
Do I throw away the data that has already been prefetched? Is that the question? I do not throw away the data that has already been prefetched. It will be ejected from the cache using the normal caching algorithm. I do, however, throw away any hints that have not been prefetched that are outstanding.
And if there's one in progress, like in the one disk case, you have to wait till it's
Yes. Unfortunately, disks right now do not provide preemptive fetching of data. So, yeah?
The graph on the left, if you were to replace the CPU that you used with a much faster CPU, do you have any feel for, since you're only overlapping CPU and I/O with one disk, do you have any feel for whether the blue bars would get higher or smaller?
Well, so if you have less CPU time to overlap and the latencies are longer, it seems like you would get less of a percentage improvement there. So. Okay, so why did I get that performance degradation for GNU-LD in the one disk case, and why is speculative execution so much less effective than manual modification? Well, there are two reasons for this, and they go back to the basic limitations of the speculative execution approach. First, data dependencies in the application. If the read request determines the next read request, if the data that is returned by one read request determines the next read request, then speculative execution will not be able to prefetch that data. And this is a major problem for several of the applications in my benchmark suite. And in fact, the incorrect hints that are generated instead are the cause of that performance degradation for the one disk case for GNU-LD. The second basic limitation is if there's too much code between the read calls, or equivalently, if there are too few spare processing cycles, such that speculative execution isn't able to get far enough ahead to get those hints out early enough to hide the latency, the disk latency. And this is a major problem for several of the applications as well. So what can we do about this? Well, they are fundamental limitations, so you can't get rid of them entirely, but there are sometimes ways that you can kind of avoid some of the effects. So in particular, maybe we can avoid issuing incorrect hints. The observation is that, or the hypothesis is that the correctness of a hint may be correlated to the code path that is executed in order to reach the read call that you then convert into hint call. Right? So if this is true, then there may be some way for us to easily identify which hints are incorrect. As an example of this, if you look at this code snippet on the left, if the speculating thread is executing this code, then it will be consistently correct in issuing a hint for this read call, because so long as the function f does not change the open file descriptor fd. However, if you look at this code snippet on the right, if the speculating thread is executing this loop, then it will be consistently incorrect in issuing a hint for this read call, because the location of that read is data dependent. So this is just a simple example of how the code path is can be correlated to the correctness of a hint. So the hint correctness prediction algorithm that I use is to extract some context information for each hint, where the context is some elements of the code path that is executed in order to reach that hint. And then during the speculative execution of the application, I retain a history of the correctness of prior hints indexed by their context information, so that when I go to issue a new hint, I can check this history of the correctness of prior hints with the same indexing information, same context information. And if the prior hints were mostly incorrect, then I could predict that this hint will also be incorrect and choose not to issue that hint, for example. So this is very similar to some of the branch prediction work that has been done in the architecture community at a high level. Now, the important thing, of course, is to pick a way of identifying the context information that is cheap to maintain and that does a very good job at differentiating between correct hints and incorrect hints. So in the numbers I'm going to show you, the context information that I use is the last 4 return addresses on the stack. This actually turns out to be extremely effective for my benchmark applications, although I can't make any wider claims. Such that, for example, generally it was the case that if a code path was, if the context indexed information for a hint indicated that it was incorrect at any time, then usually all future hints with the same context information were incorrect. So to look at some performance numbers, once again, I present performance improvement over the non-hinting original on the y-axis. And the dark blue bars, as always, are the performance of the naive design. And the light blue bars will be the performance of the technique that I've just described in each of the cases, 3 cases that I'll show you. So in this case, it is for the hint correctness prediction algorithm. And if you look at the one-disk case, you see that, unsurprisingly, since I told you that it did a very good job at differentiating between correct and incorrect hints, this technique manages to eliminate all of the one-disk penalties. However, if you look at the 4-disk case, the results are somewhat more mixed. And the reason for this is that when there are multiple disks, there's often sufficient bandwidth to hide the cost of performing this extra prefetching. Now, if there's no benefit to getting rid of those incorrect hints, well, this is a dynamic technique. It's retaining history information, so there's some overhead. And you see the effect of that for the Postgres 20% and Postgres 80%. Yes?
Is the overhead that you're getting in the P benchmark extra CPU cycles to maintain these data structures? Or is it the fact that the incorrect hints might actually turn out to be correct sometimes and you're missing that benefit?
It is the CPU cycles. I actually did a check for that. And it's just, there's an incremental cost for each, such that it sometimes causes just a few fewer hints to be issued. But the effect of that is visible because the benefit of hiding each I/O stall is actually significant. So the second technique that I tried is actually a very simple heuristic. Basically, in the naive speculation design, the speculating thread uses whatever value happens to be in memory. So it's essentially a random value. Now, sometimes this turns out to have a very bad side effect. So for example, if you have a read call that is followed by a loop where the number of loop iterations is determined from that data, well, say that the value that happens to reside in this memory location is very large. Well, then the speculating thread will never be able to complete this loop and generate a hint for the subsequent reads. This is a very simple example. So the hypothesis that I made was that, well, maybe 0 is just often a better value than the random value that happens to reside in memory. So let's have the speculating thread just assume that all the data that hasn't been read yet is filled with zeros. This is a very simple heuristic, but it's often useful to check these heuristics because sometimes they work. So in this case, for example, here it also managed to eliminate the one-disk penalty for GNU-LD. Now, how does it do that? Because after all, this technique doesn't get rid of any incorrect hints. Well, what it did was that the incorrect hints for the GNU-LD one-disk case were incorrect because the offset was data dependent. Well, now with the zeroing technique, all the offsets were set to 0, so that all the data just stayed in the file cache and no prefetching, extra prefetching needed to take place. Now, and it also had benefits for many of the applications. And this is also useful to look at the 4-disk case for Postgres, because we see that this dynamic technique can be, whether or not it's effective can also depend on the input to the application. It's not just dependent on the application itself. So Postgres 20% was much more sensitive to the loss of any correct hints than Postgres 80% because of the distance between the hints that we were allowed to issue. So the final technique that I tried was an attempt to reduce the amount of code between read calls. The essential observation was that any code that is executed by the speculating thread, which is not necessary for it to generate correct hints, it's actually dead code with respect to the speculative execution of the application. So the speculative execution would be much faster at generating hints if it could just somehow identify all that dead code and skip over it. So for example, here in this loop, I'm assuming that process data does not change any of the future data reads of this application. Well, then I could just skip this potentially very expensive procedure such that I would issue hints very quickly in the speculative execution of this loop. So the technique that I used was something that I call experimental slicing. Basically, I statically try to identify chunks of the code that might be very useful to skip. So in my case, that is loops that will not lead to a read call. And then dynamically, through kind of a very simple online learning algorithm, I test to see which of the chunks will actually be useful to skip and beneficial to skip, where it's beneficial to skip a loop in my algorithm if the loop would otherwise consume a large number of processing cycles, or if skipping the loop does not cause a reduction in the number of correct hints that will be generated. So in terms of how well this works, well, it also helps in many cases.
So you're not doing data flow analysis?
No, I'm not doing data flow analysis. You could do some simple data flow analysis, but you would often fail to, it's pretty complicated. For one thing, the kind of analysis that you need is not really up to par for binaries yet, for example. It's basically kind of slicing, program slicing. You need a very good version of program slicing.
And maybe I missed this earlier on. The regular thread is actually executing different code than the speculative thread, or they're executing the exact same code with only the main thread has to do a check to see whether it needs to do the check.
So there's two versions of the code, one with copy and write and one without copy and write. And some other modifications.
And then there's another version of the code, or the speculative version now has dynamic checks to see whether it should take this out.
Right. Okay. So this technique helps in a number of cases. What we would really like is if we could combine the three techniques and get the combined benefit of the three techniques now, right? Unfortunately, that doesn't work most of the time. So for example, if you look at GNU-LD in a 4-disk case, here on the dark blue is the performance of the naive design. The light blue is the performance with the hint correctness prediction algorithm. The purple bar is the performance of slicing and zeroing. And in this case, it's actually the performance benefit is a combination of the two separately. And then the pink bar is the performance of all three techniques. Finally, the green bar is the performance of the manually modified applications. But you'll see that the performance of all three techniques is essentially the same as with slicing and zeroing. There's no additional benefit from doing the hint correctness prediction algorithm. And the reason for this is that even though these techniques are very different on the outside, they often have overlapping effects. So as I've described earlier, even though zeroing does not get rid of incorrect hints, it can sometimes cause them to be harmless. And that's why there's no additional benefit that you see here. Yes?
So I guess that there's additional benefit caused by the linearity of the overheads. The overhead adds up, but the benefits don't add up.
There's additional benefit in terms of, yes, those hints may not be issued, but whether that translates into any kind of performance benefit doesn't necessarily translate into a performance benefit is what I'm saying.
Because I guess maybe this little question there, which is, does the cost of applying all three methods go up as the sum of all three methods, or is there a way to save the application of one if you thought it only?
Actually, I'm sorry, I couldn't hear you.
You've got three separate techniques, and if you do all of them, is the overhead involved in all three of them just the sum of the individual overheads, or is there a way to do the third one by using something that's the first two?
It's not always just the sum. It's actually sometimes even worse than just the sum, because it really depends on just how things fall out in terms of the only thing that helps speculative execution is when you generate a hint. So if you add just enough cycles to your execution that you generate one fewer hint consistently, well, then you'll see the performance impact. Whereas if the techniques separately do not add enough, you might not see it for any of them individually. So there's that. Now, if you just care about the overall performance benefit, the maximum overall performance benefit, turns out that the best combination is slicing and zeroing. And if you just care about being very conservative and never hurting your performance, well then hint correctness prediction is the most defensive technique because it actually allows you to eliminate all of the overheads. Now, getting back to something that you brought up earlier, what about the performance when there's some competition for processing cycles? Well, here I'm showing results for 3 of the benchmarks, agrep, GNU-LD, and Postgres 20%, where the y-axis here are the elapsed time, so now lower is better, and the x-axis is the CPU load that is contributed by a dummy application that just sits in a loop, in a busy loop, and goes to sleep every once in a while. Now, for each of these graphs, the lines all go to some point and then they stop. That is the point of CPU saturation. The remaining CPU load is contributed by the normal execution of the target application. And for each graph, there's a black line, which is the performance, the elapsed time of the original application, then a blue line, which is the performance of the naive design, and the purple line, which is the elapsed time of the slicing and zeroing, with slicing and zeroing, and the green line is the elapsed time of the manually modified application. So what we would like is for the blue and the purple lines to be as far below the black line as possible, as far across the graph to the right as possible. And as you can see in this, for GNU-LD, for example, you get almost to the point of CPU saturation, you're still seeing very significant performance benefits. It's only when you actually get saturated that those benefits disappear. And for agrep, this is also the case. You get very far, you up until very high loads, you'll still see very significant benefits. Now, Postgres 20% is not quite as good, but if you say when the CPU was 60% saturated, 30% from the dummy application and 30% from the normal execution of the application, well, we still see a 10% benefit. So it's So before I wrap up, I'd like to go over some related work, 2 particular categories of related work. First, there's been a lot of prior work on automating I/O prefetching. These basically fall within 2 categories. There have been a number of pattern-based approaches where the future data needs of an application are predicted by matching the current set of accesses against either some common access patterns like sequential access or access patterns that are dynamically discovered by logging and tracking the accesses to the system. Now, the difference is that these pattern-based approaches can be very effective in some scenarios, but they are not effective if your application has irregularity in its data accesses or if those accesses are not very repetitive. The second category, which I've already mentioned, is approaches based on static analysis. And as I said earlier, these approaches are very effective when they can be applied, but they can only be applied currently to looping array codes, because there are very difficult interprocedural analysis problems if they want to be applied to more generic codes. The second category of related work I'd like to discuss is prior work that took advantage of speculative execution. Speculative execution certainly is not a new idea. It's been around for a long time in the context of speculating past conditional branches in the architecture community, and also more recently for thread-level data speculation. But these uses of speculative execution attempt to actually keep the speculative execution. That's the benefit that they want to see. Whereas in my technique, the thing that I'm trying to produce is the prefetching hints. I actually throw away the speculative execution of the application because that will not be effective. It's going to be using some data values that are going to be incorrect, right? Because the data would not have been fetched from disk unless it was going to be used. Now, there have been 2 pieces of prior work that have actually used speculative execution, performed speculative execution for the side effect that it would produce. In the database community, there has been a proposal for pre-executing database transactions in order to reduce lock holding times. And the difference here was that it was proposed that this be something that the database designer would explicitly put within the system, program within the system, whereas I'm advocating an automatic technique. And then there has been some work out of University of Michigan on using speculative execution for data cache prefetching, except that in this case, we are dealing with much lower latencies, and they can actually do it purely in hardware, whereas, of course, my approach is purely in software. So to summarize what I've discussed in this talk, I've proposed a new approach to predicting the future data needs of applications. And I have developed a transformation technique that does not require any application source code or any special operating system support. I've demonstrated that this approach has significant benefits for a range of applications, and even when there's substantial competition for processing cycles. And I've shown you some techniques for making speculative execution overcome some of its limitations in terms of eliminating the single desk penalty from incorrect hints and recovering up to 50% of the missed opportunity that a simple naive design would have experienced. So that's all I was going to cover in this talk, and I'd be happy to field any more questions. Yep.
Do you know how sensitive your results are to file cache size? Is
Okay.
it the case that you bring in something that you kick out what the real thread is using?
Okay, so in my case, caching was not really much of an issue. Now, because there was always spare cache space, I guess you could say. There was always spare cache space where you would expect there to be spare cache space in a current system. And the thing was that this benchmark suite was actually formed some number of years ago. So the cache size and the data set sizes are much smaller than you would see nowadays. But I think that if you scaled it up, you would still see the same kind of missed patterns, roughly. It's not like the whole data. For example, in the Postgres the benchmark, it's not like the whole database would fit in memory. So you would see roughly the same kind of pattern.
Another question about the other cache, the hardware caches. So do you see any effects within your bottom line numbers? Do you see any effects in the hardware caches of doing this thread speculation? Mm-hmm. In other words, if you could somehow factor that out, do you have any sense of what if you, just like your algorithms are sort of free in time because you're sneaking them in when the processor might otherwise be idle, do you have any sense of to what extent the algorithms are sort of free in space? Okay, so now in terms of processor caches, it's noise. Then in terms of memory, yes, because remember that I only speculate when that application would otherwise be stalled. So if there were, for example, any other applications that were going to run, you probably would be tossing out, replacing some number of those instructions anyhow. And also, the I/O latency is so much larger that hiding a single I/O stall would pretty much cover all of those iCache misses, right? And in terms of memory, well, actually, that's something that I'm looking at right now because I was constrained by the fact that I didn't want to rely on any operating system modifications. But if you allow operating system modifications, then you can examine what will happen when you, say, for example, prioritize the memory of normal execution over speculative execution for something like that. Yes, there is an effect in terms of memory, main memory, yeah. Mm-hmm.
If you had access to the source code, what would you do and how much better do you think you could do?
Okay, if you had access to the source code, then you can do more sophisticated static analysis. Now, it's certainly the case that even with my current implementation, I did not push the bounds of what you can do currently with static analysis. And I will claim that you will often not be able to do program slicing so effectively that you can get rid of all that dead code, even if you have the source code. But you might be able to do significantly better, like for some obvious chunks of code that you can eliminate, for example. But I don't have numbers for that.
I guess following up a little bit on David's question, I'm not clear how much of the overhead organized solution is because the extra CPU time of running the speculator versus not making the right kinds of predictions that would match the manual solution.
What do you mean by overhead, by the way?
So there's a certain amount of time that your automatically modified programs are taking, and that's taking more time than the manual version, the manually modified version.
I see.
And so I'm not sure if it's taking more time because the speculator is consuming all kinds of CPU cycles, or because it's just not doing as well prefetching.
Okay, so the manually modified applications were in some cases modified to do things like loop splitting. So they were actually restructured to allow prefetching to take place earlier, right? And now you'd have to do this, to get the same benefit with speculative execution, you'd have to somehow automatically discover that kind of restructuring that would be necessary. I have an idea for how to do that, but I haven't implemented it.
Maybe like compare the hint string, the manual versus the automatic systems, and see how close you're getting.
Right, so most of the difference there, so there's two differences. One is that speculative execution normally does not get as deep. It doesn't get as many hints ahead, of course, because manual modification basically it dumps the hints as early as they can be calculated within the application. And the second thing is that there are these cases where the manually modified application will be restructured to issue hints earlier than you possibly could by just doing a straight execution, a naive speculative execution.
What's the scope of I/O-intensive applications that this doesn't help at all for?
Okay, applications where every read depends on the last read. So for example, if every read depends on user input, then there's nothing that you could...
So a web server.
So web surfing is a good example of this. Web surfing, I think history-based techniques would be more effective for that example.
Okay, thank you very much.